What if I told you everything in the universe, planets, people, light, is made of tiny vibrating strings? These strings are the fundamental building blocks of all matter and energy, weaving the very fabric of reality itself. It sounds like something out of science fiction, but this is the elegant yet radical proposition of string theory. This theory suggests that at the most microscopic level, far beyond the reach of our current technology, these strings vibrate in multiple dimensions. Imagine these strings, far smaller than even atoms, vibrating at different frequencies. Each frequency corresponds to a different particle, much like how different musical notes come from the vibration of strings on a violin or guitar. Each vibration creates a unique note. These notes are not just abstract concepts, they are the very essence of the particles that make up everything we see and touch. These notes in turn give rise to the particles and forces that make up our universe. From the smallest quarks to the largest galaxies, everything is a manifestation of these vibrating strings. Like a cosmic symphony, the universe unfolds from the music of these vibrating strings. Each string plays its part in the grand orchestra of existence, creating the harmony and complexity we observe in the cosmos. String theory is not just a whimsical idea, it is grounded in rigorous mathematics and has been the subject of intense study and debate among physicists for decades. It's a powerful mathematical framework that attempts to answer some of the biggest questions in physics. How do the fundamental forces of nature interact? What is the true nature of space and time? For centuries, physicists have sought a single unifying theory to explain the workings of the cosmos. From Newton's laws of motion to Einstein's theory of relativity, each breakthrough has brought us closer to understanding the universe. This theory of everything would weave together the seemingly disparate realms of quantum mechanics and Einstein's general relativity. Quantum mechanics governs the behavior of the smallest particles, while general relativity explains the force of gravity and the structure of spacetime. String theory, with its elegant simplicity, has emerged as a leading candidate for this grand unification. It proposes that all particles and forces are manifestations of one-dimensional strings vibrating in a higher dimensional space. The implications of string theory are profound. If true, it would mean that our universe is just one of many, each with its own unique set of physical laws and constants. If proven correct, it would revolutionize our understanding of the universe and our place within it. It could unlock new technologies and insights that we can scarcely imagine today. It could provide answers to questions that have baffled scientists for generations, such as the origin of the universe, the nature of black holes, and the existence of other dimensions. The quest for knowledge continues, and string theory stands as a beacon of hope, guiding us toward a deeper understanding of the cosmos. To understand the significance of string theory, we must first delve into the history of physics and the long-standing quest for a unified theory. For centuries, physicists have been piecing together the laws of nature, seeking to explain the universe with a single set of elegant equations. The journey began with the likes of Isaac Newton, who formulated the laws of motion and gravity, uniting the heavens and the earth under one framework. His work laid the foundation for classical mechanics, which dominated the scientific landscape for centuries. Newton's Principia Mathematica was a monumental achievement, but it was just the beginning. As we moved into the 19th century, James Clerk Maxwell made another giant leap by unifying electricity and magnetism, demonstrating that these seemingly separate forces were two sides of the same coin. Maxwell's equations not only revolutionized our understanding of electromagnetism but also paved the way for the development of modern physics. His work showed that light itself is an electromagnetic wave, a revelation that had profound implications for both science and technology. As the 20th century dawned, the quest for a unified theory took a dramatic turn with the advent of two revolutionary theories: quantum mechanics and Einstein's general relativity. Quantum mechanics describes the bizarre world of atoms and subatomic particles where energy exists in discrete packets and particles behave like waves. General relativity, on the other hand, describes the large-scale structure of the universe, explaining gravity as the curvature of spacetime caused by massive objects. These two theories, each profoundly successful in its own domain, seemed utterly incompatible. Quantum mechanics painted a picture of a fuzzy, probabilistic world, while general relativity depicted a smooth, deterministic universe. This fundamental conflict has been the driving force behind the search for a unified theory, a theory that could reconcile the quantum world with the cosmic realm. The quest for such a theory has led to numerous attempts and proposals, each bringing us a step closer to understanding the true nature of reality. String theory emerged as one of the most promising candidates, suggesting that the fundamental building blocks of the universe are not point particles but tiny, vibrating strings. These strings can vibrate at different frequencies, giving rise to the various particles and forces we observe. String theory also introduces the concept of extra dimensions, beyond the familiar 3 dimensions of space and one of time. While string theory is still a work in progress, it has already provided profound insights and opened up new avenues of research. The quest for a unified theory continues, driven by the desire to understand the universe at its most fundamental level. As we stand on the shoulders of giants like Newton, Maxwell, and Einstein, we are reminded that the pursuit of knowledge is a never-ending journey. Each discovery brings us closer to the ultimate goal, a single, elegant theory that can explain everything. The quest for a unified theory is not just a scientific endeavor, it is a testament to the human spirit's unyielding curiosity and determination. It is a journey that transcends generations, cultures, and disciplines, uniting us in our shared quest to unravel the mysteries of the cosmos. As we continue this quest, we are reminded that the universe is a vast, intricate tapestry, woven together by the threads of knowledge and discovery. Each thread, each theory brings us closer to seeing the full picture, to understanding the grand design of the cosmos. The journey is far from over, but with each step, we move closer to the ultimate goal, a unified theory that can explain the fundamental workings of the universe, from the smallest particles to the largest galaxies. And so the quest for a unified theory continues, driven by the timeless human desire to understand the world around us and our place within it. String theory emerged in the late 1960s as a radical attempt to explain the strong nuclear force which binds quarks together inside protons and neutrons. This force is one of the 4 fundamental forces of nature, alongside gravity, electromagnetism, and the weak nuclear force. At the time, physicists were grappling with the complexities of quantum mechanics and the behavior of subatomic particles. The existing theories, while powerful, left many questions unanswered, particularly when it came to unifying these forces under a single framework. Initially, it was met with limited success, but physicists soon realized its potential to unify all forces of nature, including gravity. This was a monumental shift in thinking, as gravity had long been the outlier in the quest for a unified theory. The idea that a single framework could encompass all known forces was both revolutionary and tantalizing. This realization sparked a surge of interest in string theory, leading to what is now known as the first superstring revolution. During this period, the scientific community was abuzz with excitement and curiosity. Conferences were held, papers were published, and debates raged on as physicists delved deeper into the implications of this new theory. Instead of point-like particles, string theory proposed that the fundamental building blocks of the universe were tiny, one-dimensional objects called strings. These strings, though incredibly small, held the potential to explain the vast complexities of the cosmos. The idea was that all particles and forces could be understood as different vibrational modes of these strings. These strings could vibrate at different frequencies like the strings on a violin, with each vibration corresponding to a different particle or force. Just as a violin string can produce different notes depending on how it is played, these fundamental strings could give rise to different particles and forces based on their vibrational patterns. This elegant idea offered a way to unify all particles and forces as different manifestations of the same fundamental entity. It suggested a deep and profound connection between the seemingly disparate elements of the universe, hinting at an underlying simplicity beneath the apparent complexity. The early days of string theory were marked by excitement and rapid progress. Physicists were eager to explore the potential of this new framework, and the collaborative spirit of the scientific community was palpable. Laboratories and universities became hotbeds of innovation and discovery. Physicists developed 5 different versions of the theory, each with its own strengths and weaknesses. These versions, while promising, also presented a challenge. How could there be multiple versions of a theory that was supposed to unify everything? This question puzzled many and led to intense scrutiny and debate. However, there was a problem. These 5 string theories seemed to describe different universes, each with its own set of physical laws. This multiplicity of theories was both intriguing and perplexing. It suggested that our understanding of the universe was still incomplete, and that there was more to uncover. It wasn't until the mid-1990s that a groundbreaking discovery revolutionized the field. This discovery, known as duality, revealed that these 5 different string theories were not separate at all. Instead, they were different perspectives on the same underlying reality. Physicists found that these seemingly different string theories were actually different facets of a single, more fundamental theory, later dubbed M-theory. This unifying theory provided a more comprehensive framework for understanding the universe, bringing together the disparate elements of string theory into a cohesive whole. This realization marked the beginning of the second superstring revolution, ushering in a new era of exploration and discovery. The journey of string theory continues, with physicists around the world striving to unlock the deepest secrets of the universe, driven by the promise of a unified theory that can explain it all. One of the most mind-boggling aspects of string theory is its requirement for extra spatial dimensions beyond the familiar 3 we experience. While this might seem like science fiction, it arises naturally from the mathematics of the theory. To accommodate all the vibrations needed to produce the particles and forces we observe, strings need more room to wiggle, specifically 6 or 7 extra dimensions. These extra dimensions are not some far-off realms but are thought to be curled up at every point in space, too small to be detected by our current instruments. Imagine a garden hose viewed from a distance. It appears as a one-dimensional line. However, upon closer inspection we see that it has a second curled-up dimension, the circumference of the hose. Similarly, string theory suggests that our universe may have hidden dimensions curled up at every point, forming a complex, intricate geometry. The geometry of these extra dimensions plays a crucial role in determining the properties of our universe. Different shapes and sizes of these curled-up dimensions would give rise to different physical constants, such as the masses of particles and the strengths of forces. This connection between geometry and physics is one of the most profound and beautiful aspects of string theory.